Since you're studying electricity and magnetism, the very first thing to look at is electric charge. The key ideas are that there are positive and negative charges, and I'm going to try to use the convention that positive will be done in red and negative will be done in blue. And you probably remember from chemistry that there's something called a proton, which has a positive charge, and the amount of charge on a proton happens to be 1.6 times 10 to the negative 19 coulombs. And for a negative charge, to sort of balance out the proton, we have an electron, and that has a charge of negative 1.6 times 10 to the negative 19 coulombs. Now the SI unit for charge is coulombs. One of the neatest things about charge is that it doesn't get any smaller than an electron or a proton. So the smallest unit of charge is actually called the elementary charge. And that has a value of 1.6 times 10 to the negative 19 coulombs, and it's often written as just a lowercase e. What's neat about this, and the reason why I mention it in the key ideas, is because it brings the idea that charge is quantized, which means that it comes in integer amounts or things that you can count. And then related to that is that we can only have whole electrons and protons. We're not splitting apart electrons and protons. The next big idea is that opposite charges attract and like charges repel. So if I have a positive charge, and we often label charge with the letter Q for a reason I don't know. If I have a positive charge, Q1 on the left, and then a negative charge to the right of it, I'll call that Q2, then the force exerted on 1 by 2, so I have F subscript 1, 2, and I'm referring to that, that's the force on 1 by 2, that is pulling 1 towards 2. These charges are opposite, positive and negative, and they attract. And there's an equal and opposite force on 2 exerted by 1 that pulls charge 2 to the left towards Q1. And these are an action-reaction pair for those of you who like it when I insert comments to mechanics. I know a lot of students would love to forget about mechanics, but unfortunately mechanics comes up a lot in this course, so I am going to bring it in now and then. If I mix this up, if I put a negative on the left and a positive on the right, we have the exact same effect. Like charges, on the other hand, repel. So if I have positive Q1 and positive Q2, then they repel. The force on 1 exerted by 2 tends to push 1 away from 2. And the force, I need to make that a bit smaller. One of the things that's important to note about these being an action-reaction pair is that these forces are always going to have equal magnitude. It's one pushing against the other. Similarly, if I have two negative charges, Q1 and Q2, then Q1 is going to push Q2 away, so the F on 2 by 1 is to the right, and Q2 is going to push Q1 away, F on 1 by 2. The force in this case is the Coulomb force, and they have the same magnitude. F12 is equal to F21, and the Coulomb force acts between electric charges. And there'll be more later, because we're going to actually quantify this very soon. The next key idea is that there are two different types of materials, insulators and conductors. Both of these types of materials start with atoms of roughly the same structure. So we have a nucleus, and I'm just imagining that I have a piece of each as I'm drawing this, and I just have 4 atoms, so it's an incredibly small piece. So I'll draw the nucleus in red, and then the nucleus is surrounded by core electrons. Where it gets different is in the valence electrons. If I have a rectangular piece of the insulator, I'm just going to use this black line to sort of represent the outside of it. The major difference between the insulators and conductors is that the valence electrons are free to move anywhere within the material of the conductor. In a conductor, electrons can easily move to carry charge through the material. And it's this idea of moving to carry the charge that creates an electric current. And again, there's a lot more on that later. A huge part of the course is all about electric current. But first we talk about electrostatics. Now that doesn't mean that we don't look at conductors. We just look at cases where the charges can move, but they don't necessarily move in electrostatics. one of the first questions that comes up is, how do things get charged? So one way that things can be charged is through conduction. And conductors can be charged just by touching. So if you have a neutral object, you can charge it by touching it with a charged object. So for example, if I have a block of metal and then I have a plastic rod that I'm reaching in with, if the plastic rod has a certain negative charge, and I'm trying to be careful to actually draw 16 negative charges here, because remember, charge is quantized and you can count them. So I want to make the example represent that. If I touch the plastic to the metal, then some of the charge will actually be donated or transferred from the plastic to the metal. If I then take the plastic away, the charges that were given or donated from the plastic to the metal will actually stay on the metal. Now, the charges stay on the metal, but they don't actually stay in the same place because the metal is a conductor. So what happens is that, remember, there were 4 charges there before. Those 4 charges are going to redistribute themselves. And because they're all the same sign, in this case they were negative charges, they're going to repel each other and keep pushing against each other. They're just continuously pushing against each other. So if I look at, say, the bottom left and the top left, then there will be a force on the top left from the bottom left going upwards, and there will be a force on the bottom left from the top left going downwards. And there will be a similar force for the charge in the upper right. Now if we imagine there were only 4 electrons extra, that this was a neutral metal object, except for these 4 electrons that it just got from a charged plastic rod, then each of these 4 excess electrons is going to feel an individual force from each of the other electrons. And the net effect then is that they each get pushed into their own corner. They get as far away from each other as they possibly can within the limitation of the material. They're not actually allowed to leave. It's not possible for them to leave the material. Another key idea is that charge is conserved. So when an object gets charged, there must be a transfer of electrons. Another way that objects can get charged is by rubbing. And insulators work best for this, but insulators can be charged by rubbing. When 2 materials are rubbed together, one material donates electrons to the other. And this brings us to the idea of the triboelectric series. So the triboelectric series here of glass, human hair, paper, steel, rubber, styrofoam, and Teflon is really just a very short list from a longer triboelectric series. And what's important is not whether something is positive or negative. In fact, on the list where I got this, they mentioned steel was actually neutral, so it would be like a 0 charge. But that's not really the important thing. What matters is the relative position of 2 objects or 2 materials on the list. If we rub 2 materials together, then the material that's higher in this series donates electrons to the other. And I've seen a lot of students mix this up. It's really easy to mix this up and to think that, well, if I rub glass with anything, glass will become positive. And the way I've written this with glass at the top, that would be true. But if you were to then say, well, if steel is neutral, then rubber must be negative. So if I rub rubber against Teflon, then they both get negative. And that's not true. Because remember, charge is conserved. And whenever there's a transfer of charge, then there has to be a transfer of electrons. So if you were to take rubber and Teflon, for instance, because rubber is higher in the triboelectric series, it basically means that it's more likely to lose electrons when it's rubbed with Teflon. Teflon is more likely to retain the electrons. So Teflon, between rubber and Teflon, Teflon would actually become more negative and the rubber would become more positive. Another aspect of this is that the distance between 2 materials in this series also has an effect. So the effect of transferring electrons is stronger for materials that are farther apart in the series. For example, when we compare rubber with Teflon, we had said that rubber would become more positive and the Teflon would become more negative. If we were to instead of choosing rubber and Teflon, if we were to instead choose human hair and Teflon, then the effect would be much stronger. The Teflon would still become more negative, but the human hair would actually become much more positive for the same amount of rubbing as the rubber would have been if we had the rubber rubbed against the Teflon. So again, the location in the triboelectric series does not determine whether something is positive or negative. It's really the relative positions. Human hair is higher than Teflon. It's closer, more positive, and that tells us that the human hair is more likely to give up electrons than Teflon. Teflon is more likely to keep electrons. So if we rub those two things together, the Teflon just has a field day collecting electrons. The human hair loses electrons, which is what makes it more positive. Okay, the next key idea is charge polarization. And the basic part of this is that we're separating negative and positive charges. Where students often make mistakes with this is actually in thinking that polarization can only happen in certain conditions. So first we'll look at polarization in a conductor. So imagine that we have a conductor attached to the ceiling, some metal ball. You can reproduce this, and I used to do a lab where we would basically take a piece of aluminum foil and crumple it up so we have a neutral metal ball. So neutral doesn't mean that there is no charge, it means there's no net charge. So there are protons and there are electrons in there, and that seems brutally obvious when I say it like that. Basically it means there's the same number of protons and electrons. If I take a balloon that I just rubbed against my friend's head, that's how we do it in the lab. Now that I have children, I can rub my children's head with balloons and they love it. So if we take a negatively charged balloon, which would imply that it got the electrons, the extra electrons from somewhere, and there are some electrons missing from my kid's hair right now. When I bring that balloon close to the neutral metal ball, the negative charged balloon will repel any electrons that are free to move inside the metal ball. Some electrons will actually move to the right-hand side. It actually pushes some of the electrons away by causing this repulsive force. When the electrons within the neutral metal ball get pushed to the right, that means there's going to be a region on the left that's lacking electrons. When the negative charges, when the electrons are repelled away from the balloon, that leaves a space of some missing electrons on the left side of the ball. If we add all of these up, I would get something I'll call FL, and if we add all the forces on the right, I'll have something I'll call FR. It turns out that the magnitude of the force depends on how far the charge is away from each other. So this balloon coming in here from the left with a negative charge repels electrons within the metal ball, and that pushes them to the right. As the electrons get pushed to the right, that force weakens because the electrons get further away from the balloon. And what it means then is it leaves these sort of unguarded. You could maybe imagine something like a man-to-man defense in basketball where you have these protons that are then missing their local electrons. And there's a net force to the left on each of those protons. What's really interesting then is that the force on the left turns out to be bigger than the force on the right. So without even touching this conductor, we've polarized it by separating the charge. So we have negative on the right, positive on the left. But then even more than polarizing it, because it's been polarized, there's actually a net force on the metal ball towards the balloon. The other case to look at is in an insulator. So if I have an insulator, I'll hang it also from the ceiling. Inside the insulator, the electrons are not free to move from one place to another. So instead, I look at individual atoms, and I'm just going to draw 3 of them here. If I again, imagine I'm separating this, if I again bring a balloon in from the left, and it's a negatively charged balloon, then what happens is the balloon will actually polarize the individual atoms. So the electrons are not free to move around within the insulator, but the orbit of the electron can change, and by bringing the balloon closer, you actually influence the orbit so that there's a higher probability that the electrons will be farther away from the balloon. And you end up with a similar effect. Now, it's not as extreme. On the conductor, you might have a 5 centimeter diameter conductor, and you can easily visualize that there's a 5 centimeter difference between FR and FL. Within the atoms of the insulator, we don't have any 5 centimeter atoms. It's on a tiny, tiny, tiny scale. But this effect applies for every single atom in the insulator. And what happens then is you get billions of these tiny polarized atoms. And when each one of those experiences a similar force where the right force is smaller than the left force, and you end up with a net force, again, pointing towards the left, even though it's an insulator. So the atoms are locked in place, but they end up getting individually polarized. And when you add up all of the atoms together, you get a substantial net force. Another way of charging things is charging by induction, which can be thought of as meaning charging without actually touching. Charging by induction actually confuses a ton of students, and one of the things you just really need to understand is that the sequence of events, the order in which they happen, is very, very important. So, for example, I'll show you how to charge by induction two neutral metal spheres. One of the key things is that these spheres are actually touching each other. And I know at the beginning I said charging by induction assumes that there's no touching. And in this case, I guess what I mean, and maybe should have clarified, is that the charging by induction without touching means that we're not actually touching them with the charged object. The first thing that we do is we bring a charged object nearby. If I bring that balloon close to the spheres but not touching, it will actually polarize the spheres. Now the balloon, again, it drives electrons away. It's negatively charged, so that's going to cause electrons to flow through the metal. Now the metal conductors are touching, which means that they can share valence electrons. And so this balloon actually polarizes the spheres. It pushes the electrons away as far as they can possibly go, and the result is that those electrons had to come from somewhere, and they effectively, the electrons get rearranged so that on the part of the sphere close to the balloon, it's missing electrons, and that region actually becomes positively charged. Step 2 is to separate the spheres while the balloon is still there and while the charges are separated and the charges are distributed between the two spheres. Then in step 3, we remove the charged object. So I'm going to remove the balloon, and after that, each sphere has a net charge. Now, once we actually remove the charged object, the balloon no longer influences the spheres. So these charges on the spheres are actually going to rearrange themselves. The one on the left has a net positive charge, and those positive charges are going to be attracted to the negative charges on the other sphere. Or really what's going on is that the electrons, the extra electrons on the negative sphere on the right, end up being attracted to the net positive charge on the sphere on the left. So we end up with a distribution that looks like this. Each sphere is now charged. These spheres were initially neutral and touching, and it was bringing in the charged object and then removing them while they were polarized that ended up giving them each a net individual charge. The last thing to discuss when talking about charge is Coulomb's law, and we're finally going to quantify that force, the electric force or electrostatic force. So Coulomb's law, I'm going to show it to you in two different ways. The first way, we'll just talk about the magnitude first, and the magnitude of force on charge 1 exerted by charge 2 is equal to this constant K times the charge, the value of the electric charge on the first charge, times the charge on the second charge, divided by the distance between them, so between 1 and 2, squared. K is a universal constant, a physical constant, and we're going to explore that a little bit more later on, but for right now, it's simplest just to think of it as a constant and understand that you can use 9 times 10 to the 9. That is an approximation. I think the actual value is 8.998, but even to 3 sig figs, it's 9.00, so we can just use 9 times 10 to the 9. And then my notation of F12 is the force exerted on Q1 by Q2. And this is the expression that we use to find the magnitude of the force. And in this chapter, in your course, you'll probably spend about half of your time working with Coulomb's law. And the other, even though it's a small part in terms of the video course, and even it only gets one section in the book in your textbook, but It's just that we end up using it to quantify a lot of different problems. You still need to have the understanding that opposite charges attract and like charges repel, and that's actually where I recommend you go to find the direction, because the direction of the force, remember force is a vector, so it has magnitude and direction. The direction is that the force will be towards the other charge if the charges are opposite, and it will be away from the other charge if the charges are the same. And that's pretty much all you need to know for Coulomb's law. There are lots of different ways in the problems to give you certain variables, and then you have to solve, and sometimes you have a quadratic because you might be solving using the distance, etc. That ends up being just a bunch of different particular problems, and we'll look at some of those, but this is the basic idea. There is another form of Coulomb's law that's worth taking a look at. And for this, it's going to depend, I think, on your teacher. You might choose to do it this way if you prefer. I know when I was doing it, I preferred to work with the magnitude separate from the direction just because I felt that it separated the physical understanding. But there is a sort of mathematical simplicity, or maybe beauty, dare I say, to expressing it this way. When I express Coulomb's law this way, we again have R12 squared, we add a unit vector, R12. And this is effectively exactly the same thing as what we had before. The difference is that we have this unit vector. The unit vector is used to show the direction of the force. And we notice that we also don't have the absolute bars around Q1 and Q2 because those are actually now necessary for this equation to work out. So if I draw this, I'll have, say, Q1 right in the center there, and I'll have Q2 down and to the left. To define the direction for r hat, I want it to be away from Q1 and on a line that is away from Q2. So this unit vector would be on that dotted line. Okay, so how does this actually make sense then? If Q1 and Q2 are the same sign, then you would have, say, positive, positive, or negative, negative, and that whole expression in the middle, KQ1, Q2 over R12 squared, ends up being positive. So if they're both positive, both negative, you end up with a positive R12. And that makes sense with R12 going away from Q1, because if they're both positive, they repel, and the force on Q1 is away from Q2. If they're both negative, again, they repel, and the force on Q1 pushes it away from Q2. So those positives multiply together to give positive, or the negatives multiply together to give a positive, and that's how it works. If only one of them is negative, which means that they're opposite, then you end up with the force vector being negative something times r hat 12. And in that case, if one of them is negative, that is when you get the force moving in the opposite direction, so that the unit vector would still point away from Q2, but if they are of opposite sign, then the direction of the force vector will be towards the other charge because they're attracted. And once again, if the charges have the same sign, then they repel, and the force on Q1 is away from Q2 in the same direction as r hat. The quantitative applications of Coulomb's law are fairly straightforward, so where it gets tricky is in having multiple forces, in which case you just add them up. You can have them in strange configurations in 2 dimensions, maybe 3 dimensions, and the key thing that I would suggest there is to always show the force direction. So always do a sketch and always show the force direction when you're solving problems. And that's going to be true regardless of whether you prefer this form or the other form of Coulomb's law. They're pretty much exactly the same thing. As long as you draw the sketch, show your force directions, then you're almost certainly going to get the right answer. And that's pretty much it for the first chapter in Coulomb's law.